Good day, everybody. It is time for projectile motion, the real deal, the whole thing, not just these limited pieces of horizontal projection, only launched from the ground. Obviously, in everyday life, things can be launched at any angle from any initial height, right? So that's what we're tackling today. Before we get to that, let's go over the challenge question that was just for yourself, not having to be submitted. We had an object being launched. We want to know what velocity it needs to be launched at 60 degrees, at an angle of 60 degrees, so it lands 20 meters over. So as a hint to work your way through this, if you want to try it some more, and you can press pause and so on, of course, we could look at what we did for, how far it lands when you're launched at a known velocity. First thing we did, of course, was componentize velocities, right? The only difference now is we don't know that velocity, so just leave it as v, right? That's how math and algebra works. That's why there's letters in algebra in math, so we can represent unknowns, right? So we've got v cos theta for the x velocity and v sine theta for the y velocity, and so we have those components based on that, and then as always, realize that they don't mix, right? You got to make sure to use the x velocities for the x displacement stuff and the y velocities for the y velocity stuff. So only acceleration only occurs with these ones. These ones are just uniform velocity rather than uniform acceleration. Okay. So basically, at this point, you're given the y direction stuff. We know we started at the ground, end up at the ground. So we have the displacement 0, and there's information we have, right? So we have the velocity as an expression at least. We have the acceleration. So basically, do something that makes do our normal work with that stuff as much as we can, and you're given a bunch of x information as well. So do something with that, right? So do the normal work and see what happens. That's the way to get through this, right? Is just start to calculate stuff. You don't necessarily have your whole path in mind all the way from start to finish to get the answer, but you have to be able to just try to work your way through it. Okay? And that's the key to that, getting past the blank page that's in front of you. So what's something we know about the horizontal information? Well, we know the displacement in the x direction needs to be 20. That's y by accident there, but x direction is 20, right? We want to end up over 20 meters. And we know it's uniform velocity. And so we're going to have velocity in the x direction equals the displacement in the x direction divided by time. So we have this equation. We have the velocity in the x direction as an expression, the displacement, and the time. Obviously, in this, there are two unknowns, so we can't solve that thing at this point, right? The vertical information. We've got the initial velocity as an expression. We've got the final velocity as an expression, because we know what goes up must come down kind of thing. And we have the acceleration, right? So from that, we could actually go ahead and get time, I suppose, right? Yeah, we could actually go ahead and get time there. Wasn't what I was thinking of saying here, but oh no, we can't because we don't know v, right? Okay, so we have we still have two unknowns. So again, we have two unknowns, but here's where the math kicks in, right? Where we have two equations with two unknowns, right? We've got this equation here, and we have this equation here. So we have two equations with two unknowns, right? We've got two equations, two unknowns, just trying to emphasize what the idea there. And so I don't like what I did there, actually. It just doesn't look good. So, star with the circle there, star with the circle there. Equations 1 and 2, we have two equations, right? And so substitution elimination will work for this, right? And the talk I like to give to students is usually the reaction at this point is, oh no, not that substitution elimination stuff. How am I going to ever remember that? And so on and so on, right? Well, you're in grade 11 right now. So yeah, reviewing grade 10 work and getting it under control is a challenge, maybe. If you remember it, great, go for it, right? But what you want is eventually for that to be a good thing, that substitution elimination comes up. Because really, if you're working at grade 12 level or university level or to get your PhD or something, all you have to do is substitution elimination. That's just grade 10 work. That should be a good thing, right? And be like, oh, cool, I have that skill set already. I can go ahead and, hammer my way through that. So let's do that, right? We've got these two equations, and so we're going to, solve for one of the variables. So what did I do here? I got my time multiplied on both sides. And then my velocity. So I'm isolating for the time, right? It doesn't matter which I'll isolate for. I'm looking at this and wondering why I didn't just divide out the cos 60 and have v isolated for it, but then you'd have fractions. So, anyways, I guess we have fractions anyways. Just the way I chose to do it. Okay, so delta t gets substituted in here, right? So we end up with delta t, the 20 over v cos 60 in there. And so then we end up with inverting and multiplying, and we end up with just a v in the equation, right? So we have this, we have the negative 9.8, the 2v, now the 2v times another v, so you're obviously going to have like a v squared. We're going to have a sine 60 times a cos 60, those are all just numbers, right? So we can just start working things out as we go through this. And so what did I do first here? I guess I divided out that 2 and then multiplied by the 20, just to simplify things a bit. So that's going to leave me with just v sine 60, v cos 60. So it's going to be a v squared and then whatever sine 60 times cos 60 is, right? So the 0.433 from the sine 60 times the cos 60. Hopefully that they follow along what I'm saying there, right? That is this. Everything else went to the other side. And so now, of course, I can just divide both sides by 0.433 and end up with that. I didn't show the step, but I can do that here. So divide by that 0.433. Maybe I'll use it for, go back to my green idea here. So divide by that 0.433. And so I have that number, and then I just have to do the root of both sides. Okay, so I'm getting that the velocity needs to either be positive or negative 15. Obviously, we want to launch it with a upwards velocity, so you probably take that positive as the answer, right? So therefore, it should be launched at 15 meters per second, right? So the flash applet doesn't work anymore, but we've got other simulations that can do this. So let's look at this one here first. So here's a little applet that shows a cannon launching a thing, and they don't actually factor the size of the cannon into the calculations, which is what we want. So launching at 15 at an angle of 60, and you launch, and you see if it hits that 20-meter target, and it does. 3 stars. In the applet here, pause, I guess, reset. Ooh, did I want to do that? Yeah, we're good. So start, and it launches, and of course lands at the 20-meter mark, and so on. Okay, so we figured out the right velocity. Okay, so that's it's a challenge question for sure at this point, but at the same time, it involves the skills that we know. Componentize velocities, even though you don't know the actual value of the velocity. Work with the idea that the horizontal information, the horizontal displacement, and it's constant velocity. Work with the vertical stuff, and that. We could have even worked with delta. The y direction displacement is 0. It just would have been a different version of an equation, and would have been a slightly different substitution elimination. So you could try that as a challenge. Like a extra challenge. What is the delta d y equals 0 equation? Needs 2 stuff, right? This is going to be 2 equations, 2 unknowns as well. Or actually, it should just said 2 unknowns, right? And so this would be an alternate equation where you have like equation 3. Well, what happens with equation 1 and equation 3? Should be able to get that same answer, 15. Right? If you go through that and you get 15, you're on the right track. You can tackle anything, right? That's the goal. All right, so the final frontier here for this, the final whole kit and caboodle, if you will. We've got a height of 4 meters and launching at a velocity at an angle. Okay, so picture this situation here where we got the 4-meter height we're launching at, 48-degree launch angle, launching at a known velocity, and the usual questions. How high did it go? How far, how long did that take? How far over was it? Often people ask, like, when did it get back to its initial height? When did it get to the ground? When did it get to some other height as well? So picture, H1, let's say, or H2, right? When did it get to these other heights as well? I think I forgot to end up including that in the last lesson. I thought about it and then I got distracted, so I probably should include one of those here. I mentioned in the last video that you can tell there should be 2 answers, right? So there should be 2 answers for this one, and there should be 2 answers for this one. And this answer would be like a negative t, showing that, instead it could have been launched from the ground earlier, and it would have gotten to that height, and so on. All right. So let's go through it here. So all the different things we know and whatnot and can do. So we know we were launching with an initial velocity of 7.43. I think I went ahead and did the components somewhere. Where did I do this? Velocity components. So the x component, the y component, of course, right? Well, that means we have an initial velocity of 7.43. It goes to the top, and then it comes back down to the initial height, and then it falls 4 meters, right? So if we're going to put information on this, we know that this spot there is that it's at the top, right? I better not do that, right? So this one in the middle here is where it's at the top. I'll do this. It's more obvious what I'm pointing at there and which label. And then that same amount of time, right, would match as well. Just if we verified that in the past. Later on, it lands. We have that same initial velocity, just in the negative direction. These are all things that are known, right? So the other thing we should point out is that this overall result, decide how I want to show this. Basically, let's just put it this way for now. We've got displacement equals negative 4 meters, right? Because we end up at the ground, which is 4 meters below where we started. So that can be thought of as the positive triangle and the negative triangle. So the positive triangle and the very big negative triangle. Or it can be thought of as this section here. Okay, so this could be your delta dy. Okay, so this would combine, right? You have a positive number plus a negative number, and it would combine to be -4. This would directly just give you -4. So basically, this is your VT graph method, and this is your equations. How that would make sense, right? All right. So let's tackle this here. Maximum height and when. So basically, we're looking at a mini question as a part of this, right? So what do we know for maximum height? Well, you got to identify that key information, right? We've got our initial velocity up of 7.43. We've got an acceleration of -9.8, and then we know the final velocity if we want to think of at the top, right? So final velocity would be 0. And so we'd have this information. So it just wasn't as good back then. This last time I taught this course is, listing that information. But here we go. So I probably would have said it, but just didn't write it down, I guess, right? When I did the file originally. So V1y equals the 7.43. The acceleration equals -9.8. Let me just arrange to make a little bit of room for this stuff. And the hidden information here was that V2y equals 0, right? So we're at the top. So that's where this is coming from. That's the 0 there. And so basically, your delta V is -7.43. And yeah, we just can calculate out the time, no problem, right? If we want to get the maximum height, we could just get the area of that rectangle, nice and easy, or we could use equations, put the numbers in and calculate it out. Okay. So uniform acceleration question skills kicking in for this first part of the way answer, maximum height we get to and when we got there. Right? If we want to know how far over it was and reached maximum height, well, now it's just a uniform velocity, right? You have to recognize that this is uniform velocity. There's no acceleration. Just because it's accelerating vertically doesn't mean it's accelerating horizontally. And so velocity equals displacement over time, boom, boom, get the number, right? So it's over 5.07 meters when it's at its maximum height. And how far over does it land and when does that happen? And so the key information for when it lands, right? So when does it land is right here, right? When you land, in this situation, you're down 4 meters from where you started. It doesn't matter that you went up in the process and then came back down and then went down 4. That's just all you have to do, right? So if you're looking at this picture here, of course you deal with the amount up you went and so on, right? So this part here would be the amount up you went and so on. But in reality, this is just, you can just cut right to it and do it. But both ways work. It's just the equation method, and knowing the displacement is -4 brings you right to the answer. Okay, so we select an equation based on knowing initial velocity, acceleration, and displacement, and we want the final velocity. So we plug numbers in and we solve, and we get that final velocity. Notice if I tried to get time first, right? If I tried to get time first, I would have to use a quadratic, right? So first we're going to do this. V2 first equals quadratic work. So you can choose to avoid that to make your life easier, right? Not that we can't, it's just, why would we? Work smarter instead of harder, right? After that, you just have, V1, V2, and acceleration, so you can get the time, no problem. So this is the velocity it has vertically, right? This is V2y. So it's not the velocity, it's the y component of the velocity. Notice that the root would have been plus or minus, right? So when we do the root of both sides, I don't like that. When we do the root of both sides, we'd have a plus or minus answer. The minus is the one we're choosing because, of course, it's down, right? So the math gives us those two options, and we choose the one that makes sense. And then, yeah, delta V, delta T, and so on, solve out, we get the time. Right? Obviously, then we can figure out how far over it lands as well. Same deal as before. We got that uniform velocity of 6.69 meters per second sideways that entire time. Air resistance is negligible, all those things, right? So therefore it lands this many meters over, and so on. The velocity it hits the ground with, well, we know now some information, right? We have this velocity of 11.56 down, so I don't have a negative in there because I'm saying down. And I've got that velocity that it has sideways the entire time, so it still has that. And so the root of the sum of the squares and tan inverse, boom, we get our numbers. So the final velocity hits the ground with is 13.4 meters per second at 59.9 degrees below the horizontal, having gone to a height of and having traveled over and so on and so on, right? So that's the reality of how this all works. If I go back to this, I can put the initial height in as 4. Set here. The initial height in as 4. The initial speed in as, what's our speed here? Speed of 10, angle of 48. 10, angle of 48. And mass doesn't matter, gravity's proper, and we just say start. And it goes and goes and goes and lands. And so it landed over the 13 meters. It took 1.936 seconds total. I don't know if we calculated that. I don't remember. And so on. If I show the velocity, it even has this 13.4 meters per second at 59.9. Like it's right. It works. It's, you know, obviously this program's a simulation based on these calculations. So of course it works if we haven't made a mistake, but it also does match real life as well. Yeah. So yeah, that time we did have it right because we had how far over 1.93 seconds, matching that 1.93, you know, give or take, rounding errors along the way. And then the new question that I'm going to add on the fly here is one of these guys, right? And so let's just grab that for now. I'll modify it. And so we can make a question here because we know some things, right? So we know that the maximum height it got to was maximum height, and when this maximum height of 2.82 is above the original, right? So I should have, you know, we said at the time right there. So the max height is 2.82 above the cliff, above the ledge, or whatever, you know, whatever it's at, right? So in other words, we're talking about it's 4 meters, right? So 6.82 meters off the ground. Okay, so that's just something I didn't mention back then, but should have been hopefully fairly obvious, but sometimes not. So make sure to clarify, I guess, is a good idea. And so what we can do for this then is we have that 6.82 meters of height, right? So if I looked for a height of, say, 5 meters, then the work should spit out an answer, two positive answers, right? An answer for here and here. And if I were to ask, say, like, when does it get to a height of, say, 2 meters, then it should spit out a negative time and a positive time. Positive time is going to be a little bit before that one, right? So let's go with, well, either one of those was fine. I almost think maybe I'll go with this one because of that interpretation of that negative is weird, whereas this one's just going to spit out two correct answers, right? So what do we know in this situation for this question? So the question is, when does it get to a height of 2 meters? Right. So the given info is what? We have our initial velocity in the y direction, because the y direction stuff's the stuff we're obviously going to have to work with because we have the acceleration and so on, right? We have that initial velocity. I'll go back and gather, remember what it was in a bit here. We have the acceleration, and of course we have that displacement, that new question, right? So we have the displacement equals what to get to there? Our displacement is down 2 meters, right? So negative 2 meters. So notice that it's negative because it's down 2, right? Down 2 from the initial, yeah. So initial velocity was, run back and see what that was, 7.43. Meters per second. And just pause quick because I got to grab a UASIM for us. All right, I'm back. All right, so we've got V1, and we've got acceleration, and we've got displacement, and we want to know when it lands there, right? Now we could work on we could do the velocities first, I suppose, and work our way through things. So if we did that, then you see we'd be getting two answers from that. So that's probably the way we should do this, I guess. So to get that final velocity, if we did that first. So the question was like delta t equals, but we could do v2y first. In which case we'd work with just, solving, and that would give us our plus or minus answers. If we did this one first, so if we did the v2y first, change this to a color here. Let's do purple, and I'll make this one purple as well to show the idea. And then if we went with this, what we were originally asking for was just for the time, then we would have had this one would have all four, right? And so you have a choice. You can do delta d equals v1 delta t plus 1/2 acceleration delta t squared, in which case you've got displacement and v1 and acceleration, and so you have a full-on quadratic, right? Full form, or you don't want to use the quadratic formula. Instead, you could get v2 first. In which case we'd have our v2 squared equals v1 squared plus twice acceleration delta d. Technically, we don't really want vector symbols on there because it's a little bit of a gray area where we're talking about vectors but squaring, and we haven't really officially done that yet. Cross product and dot product and so on. So we're talking about the magnitudes there, really. So let's do the v2 one first. So let's get v2 equals v1 7.43 squared plus twice negative 9.8, and we have the down 2, and so we've got numbers here to calculate. 7.43 squared, 55.2049. And then we have two negatives, right? A negative and a negative, making a positive. So we have 2 times 9.8 times 2. 2 times 9.8 times 2. Or 4 times 9.8 if you wanted to save button strokes, 39.2. So we've got that. So 39.2 plus the 55.2049. Uh-oh. 0.2049. There we go. 94.4049. And so that's what v2 squared is, of course, v2y squared. And so we root both sides. And we're getting an answer here of root of that thing. Get plus or minus 9.7162. Okay, so plus or minus 9.7162. And of course, what the plus means was when it was on the way up, and the minus is on the way down, which at this point for this one you might not have even thought of that. You would have just used this one, of course, because that's what actually happens, right? And then after having done that, we could just say, okay, well, then we could do both cases here for this. We'd have acceleration equals delta v over delta t, and acceleration equals delta v over delta t. So we'd have, I guess I should have done like v2 minus v1 for both of them. Kind of like the idea of doing this one as first as well, because it'll literally spit out a positive answer and a negative answer, right? In which case, the negative means that before you launched, and the positive is the one that actually happens. So if instead you launched from the ground, the negative one actually sort of does have a meaning. But let's just go for it here. So we have our V2. So let's do the on the way down one here. So because that's the one that's like the actual situation, right? So we've got the V2 is the negative 9.7162, taking away the initial velocity of the 7.43. And we're looking for the time, and we know that it's negative 9.8. So you solve out for time. The other one is going to be the positive 9.7162 minus the 7.43 and the negative 9.8. Right? So we're going to have the 9.7162. Might as well just use that, I guess, extra decimals. And we have, oops, I want to subtract the 7.43. So I have that didn't work out, did it? I thought I had a negative in there already, but I guess not. So 9.7162 and the 7.43 combines to 17.1462. Negative 17.1462 over, and I'll just do the math steps quick here. We're obviously multiplying delta t both sides and then dividing both sides by 9.8. So I'm just going to do it here. I've shown enough work enough times. We have that thing divided by 9.8. Gives us 1.749. So after 1.749 seconds, remember it took a total of 1.938 to land. So it got to the height of 2 meters before that. So the numbers are reasonable. They seem to work out and make sense. Versus, or in the end here, of course, we got to look at the result for this one. And so we have the 9.162 take away 9.17162 take away the 7.43. I think I had this number before by accident, the 2.2862. 0.2862. And same idea, we're going to multiply both sides by delta t and divide both sides by negative 9.8. So we have that thing divided by negative 9.8. So if you really want to use a plus minus, you can, the negative 9.8. I don't know I'm not sure how to use the plus minus button. That's because I wouldn't normally use it. But we get a negative answer, of course, right? We get negative 0.23. So if you really want to see it that way, you'd have to use it properly, use the negative button properly. Yeah, 0.233 seconds. And so this would be this would be the negative 0.233 seconds. And this would be before the 1.98, we have that 1.749. Obviously a therefore statement to do with that kind of thing could be constructed, and it works. Okay, so for yourself, you could do the quadratic formula here. If you want to set it up, delta t, oh, actually I didn't do the equation even yet, did I? So the equation would have had what in it? Would have had a -2, would have had a 7.43, and it would have had a 1/2 of a 9.8. I guess I need to do a little work to even just set it up. Let's just leave that there and put some of the numbers in place. So we'd have a -2, we'd have a 7.43, we'd have a 1/2 of the 9, negative 9.8. So we'd have a negative 4 point, just so you're not stressing out about numbers here, right? Divide by the 2 and you get your 4.9 that you'll get used to seeing as you go, but I don't want to just seem like I'm pulling numbers from nowhere here. And I forgot, if you're watching and thinking, hey, wait a minute, what about the delta t from this part? Don't forget that, right? And so we'd have the quadratic would be the negative 4.9 delta t squared plus the 7.43. And then add 2 to both sides, and you get your quadratic, right? So there's your full-on quadratic that you'd have to use your A, B, C, and do the quadratic formula. So there's your A with the negative, your B, and your C, and the quadratic formula spits out the same numbers. So just double check and see, but it's kind of optional for the course, so I'm not going to go through it. If you want help with it, let me know. I can help you with it by a video in the help section or whatever. So, but that is a long enough video for now. So all for now. Thanks for watching. Talk to you later.